Hi, I'm Professor Craig Beal from Bucknell University, and this is my video tutorial on sensors for measuring motion. When we're designing a sensor to measure the motion of an object, we have to consider the degrees of freedom of that object. So an object that's free-flying in space has 6 degrees of freedom. We have 3 translational degrees of freedom, so it can move up, down, left, right, in, and out, depending on how you're looking at it. It can also rotate. So it can rotate around this axis, around the second axis, and around the third axis. And so that gives us 6 total degrees of freedom. Now, in each one of these degrees of freedom, we also have the ability to look at the position, the velocity, or the acceleration of those degrees of freedom. The challenge here is that we need to consider our reference frames. When we talk about the position of an object, we're talking about where it is relative to something else. Typically, we consider that to be an inertial coordinate system like the Earth and some fixed point on the Earth, but it could be some other relative position. If we have some moving object like a car, for example, and we're interested in the position of something within the car, then really what we're asking is, if we have one reference frame, where is some object located relative to that reference frame? Even though that reference frame itself might be moving with respect to the ground. So we have some sort of velocity with respect to ground, and then our object is moving relative to that. So we can make measurements from a bunch of different reference frames, and we need to be clear what reference frame we're using. For some of these, this is fairly easy. I've given you the example of the linear position. So this one's not too hard. We can take some position. We position one part of the sensor on the object we're trying to measure, and we position the other part of the sensor on the object that's the reference frame, and we use a measurement between those two to determine where the object is in space. Velocity gets a little bit more challenging. So if we pull this out here, velocity gets a little bit more challenging. It's effectively the same problem. So we have some reference frame here. That's our global, and then we've got some object that's moving. The problem with that is that as this object is moving, it's getting farther and farther and farther away from sort of our zero reference point. And so it's relatively easy to measure the velocity of something that's just going by a particular point, but it's much harder to measure that velocity continuously because your two parts of your sensor are getting farther and farther and farther apart. So that's another challenge here. The last part that we can think about is an acceleration. And an acceleration is yet another type of problem. In terms of acceleration, we actually can do a little bit because we can develop inertial reference frames. That's relatively straightforward. So we have an inertial reference frame, and rather than letting an object move, and we'll talk about this on the coming slides, we can measure the acceleration of that object due to the force it exerts on something else. If we allow it to move relative to the reference frame and we apply some sort of spring or other flexible element, we can allow that mass to move, and then we can measure a force. And so this one's a little bit easier than the velocity because it allows us to keep the two parts of the sensor in a relatively small range relative to each other. So let's move on and talk a little bit about how each of these different sensors work. Let's talk first about displacements of objects. First, we'll go with the angular case. That's a little bit of an easier one. So to measure angular displacements, we have a number of technologies. So we've talked about some of these before. we can use things like a potentiometer. And you'll notice that with this potentiometer, there are a couple of key features. So here we have what's referred to as a panel mount potentiometer. So you see that there's a set of threads here that go with the nut and the washer that are seen on this. And those threads allow you to mount this thing to a stationary panel. And then you'll also see that there's a small pin here, which acts as a key to make sure that the potentiometer base doesn't turn. The stem of the potentiometer then can go to the other part of your device that's going to be rotating, and you can allow this thing to have some relative angular motion and measure that motion. Another way that you can measure angular motion is through the use of an encoder, which we've also talked about before. So an encoder, and in this case the encoder is a through-hole encoder, allows you to mount the body of the encoder with tabs, screws of some sort to the stationary base. And in this case, the shaft goes through the hole in the encoder, and this white portion rotates with the moving object. Now, the nice part about the encoder is that there aren't really any motion limits, especially if you consider an incremental encoder, as we've talked about before. The encoder can continue to turn and turn and turn, and you get more and more counts. The potentiometer, you have to be a little bit concerned about the range, because the potentiometer can only turn so far before you run out of track on the wiper. You can buy multi-turn pots, but you don't have the ability to go continuously around and around and around. On the linear displacement side, we also have reasonably good technologies. So, for example, we've talked about the linear analogs to the angular technologies. So we've talked about having encoders. So here's a linear encoder. In your book, you saw the LVDT, which is a particular coil technology. LVDT, a particular coil technology that allows you to measure the displacement of something. Let's get this on the slide too. In encoder. Another technology that we didn't talk about, but is sometimes useful to measure displacements over a larger distance, is something that we refer to as a string potentiometer, or a string pot. In this case, you use a rotary potentiometer, in this case probably a multi-turn potentiometer, or something that's geared down so that you get a small number of turns, and you can pull a string out, which causes it to rotate, and measure how far the string has been pulled out of the device. And lastly, a technology that you've probably heard a lot about, but maybe haven't really explored, is GPS. So GPS uses a set of satellites. We refer to this as a constellation all around the Earth. And those satellites are stationary relative to the Earth itself. And the position of those satellites is very precisely controlled. So a roving device on the Earth receives a signal from the satellite, and from that signal, the device can calculate how far away the satellite is. If you take 4 of those satellites and you compute the position to each one, and you know the exact position of each of the satellites, then using that, there is only one unique point on the surface of the Earth where you could possibly be, and that's the intersection of the spheres that are the appropriate distance from each satellite. So this is a nice technology, and it allows you to get displacements over an extremely wide range, although your precision is a little bit less tight than it is for some of these other local sensing technologies. Measurement of velocities is a bit more challenging than measuring positions. And the reason for this, as I mentioned on the first slide, is that you need a reference frame, and as something is moving, it typically gets farther and farther away from the reference frame. So if we think about this as being our inertial static reference, and we've got this object moving away from our sensor, then this measurement gets larger and larger and larger, the distance. And so it's harder to have a fixed body measuring the moving body. So one way that we get around this is by having the stationary bodies be much, much, much farther away. For example, in the case of GPS, and we put some sort of rover. So we have our rover vehicle, and we have our satellites. So let me add a satellite here. And the satellite sends a signal to the antenna. And so with it being far enough away, you can still receive the signal via the radio link, and you can figure out how far you are away from the satellites. And therefore, you can also differentiate that and figure out your relative velocity. There's also another GPS technology which allows us to do this even more directly, and that is a Doppler shift measurement. So the radio frequency wave that comes from the satellite to the vehicle has a particular set frequency. However, if the satellite and the vehicle are moving, or the vehicle is moving farther from the satellite, then that wave appears to have a slightly lower frequency than if the vehicle were moving or stationary, or the vehicle were moving toward the satellite, at which point it would have a slightly higher frequency. And this is the Doppler shift effect you see or you hear with an ambulance siren, for example. When it's coming closer to you, you appear to hear the frequency increase. It gets higher and higher pitched. And as it goes away from you, you end up hearing it getting lower and lower pitched. By directly measuring this Doppler shift, you can actually get a direct measurement of the velocity via GPS. So this is one technology that works. Another technology that can work is to use a camera. And the idea here is to flip the idea of the rover versus the stationary object. So we assume that we have some sort of stationary road. We've got our rover, our moving object, and we've got the camera looking down and seeing the stationary object. And if we take a whole sequence of frames, then we can look at a frame at a time. And if there's a particular object, let's say there's a little star that we can measure in the frame, and in a sequence of frames, we see that object moving from left to right, up, down, whatever it happens to be, we can turn that into the idea that this is moving in a frame and that we have a velocity. This is referred to as optical flow. The technology works relatively well, except that the camera is subject to any sort of occlusions. So for example, if you put this on the bottom of a car, you're going to get mud and dirt on the camera, and as the camera gets dirtier and dirtier, your velocity measurement is going to get worse and worse. It also tends to be relatively expensive, as does the high quality GPS that you need to do this for high precision GPS applications. On the angular side, again, we run into the same problem of being able to make a direct measurement as something rotates around. Obviously, because two objects, if they share an axis, if we can put the stationary part of the sensor and the moving part of the sensor on the same axis, they'll rotate around and around. And so we could use this relative rotation, but again, we'd be differentiating a position measurement if we used an encoder or something like that. So we actually use a trick with angular velocities, and we take advantage of the fact that the angular velocity produces other effects. And so we use a sensor that we call a MEMS. So that's a micro electromechanical system gyroscope. And so this MEMS gyroscope involves having a rotor that is suspended off of some fixed base. And within that rotor, you can see that we've suspended some sort of a small target mass, and that target mass vibrates back and forth. And the reason that we do this is that as if this is not rotating, the target mass just bounces back and forth in its original line. However, if we have a rotation in addition to this velocity, that's radial velocity, that produces a Coriolis acceleration. And the Coriolis acceleration is going to want to cause the mass to displace to either the left or the right. And if I bring in another schematic of this sensor, you should be able to see why this works. So we have an inner frame and an outer frame, and then the sensor that bounces back and forth. And as that gets displaced, it causes the displacement of this inner frame to the left or the right. And if you see all these little fingers that go between the inner and outer frames, those fingers act as capacitive sensors. So each finger is an electrode. If you have a dielectric medium in between them, including air, you're going to see some signal that comes from the fact that these electrodes are moving closer or farther away from each other. And by doing this, you can correlate that to the amount of, or the rate of rotation that you're seeing from the gyroscope. Lastly, we'll cover accelerations of bodies. Now, the angular one is easy to handle. We'll do that first. So the angular acceleration of a body is something that is challenging to measure. There's basically no direct technology for this. So right now we'll call this sort of an open question for sensing the general angular acceleration of a body. Now, you know from physics that we could do something like this, where if we have a body that's rotating along a known axis, then the angular acceleration is just equal to the linear acceleration times the radius. And so we could stick an accelerometer on the disk, or a disk, and we could measure the tangential accelerations of the object, and we could work out from that what the angular acceleration was. But in general, we'd like to stick an angular acceleration sensor onto a body and measure its general angular acceleration. That is, we don't necessarily want it to be along a particular axis, but we just want to know what is the angular acceleration of this body rotating through space. And that's a much harder problem in general. Sensing linear accelerations is a technology that's a little bit more established. And with these linear sensing, we can take what we refer to as an accelerometer, and we can place it on the object that we want to measure the acceleration from, and we can get a direct measurement from that sensor. And the way that these accelerometers work is by using a suspended mass. That suspended mass, right here in this diagram, is attached to a casing, an outer casing, by means of some sort of spring and damper system, so that the mass is free to move, but within a certain range of motion and with certain predictable dynamics. An acceleration of the motion of the casing causes it to move relative to the mass, which is actually serves as the inertial or stationary reference point. As that casing moves relative to the mass, it creates a displacement, and we can measure that displacement. In this case, they're showing the use of some sort of potentiometer to give you a variable voltage. But in reality, a potentiometer would be a poor choice here. You'd want to use a non-contact sensor like a capacitive sensing technology so that you don't affect the motion of the mass itself. By doing this, we now have the ability in a small device to measure the impact of acceleration, create an electrical signal, and therefore get a proportionate measurement, electrical measurement that represents the acceleration. Now, the device that you're seeing in this diagram is a relatively simplistic one. We can use something a little bit more compact as well as integrated to do this. And so you'll find a number of sensors available on the market, such as this ADXL 345 digital accelerometer. This has a multi-axis accelerometer built in, and that allows you to basically sense this in 3 axes. Furthermore, these are built with, again, micro electromechanical systems. And so we don't actually fabricate separate springs, dampers, and so on. What we do is we fabricate some sort of a flexible element that makes it sort of all in one. So the flexible element you see in the orange here. So by having a large body, it has its own mass. And by having relatively thin sections that attach to anchor points at the edges, it creates some sort of flexibility. And so you get the mass and the spring all in one. And then if you put in some fixed plates with these fingers here, you can actually get your capacitive sensing out of the exact same piece. And so you have basically no completely moving parts here. You just have some parts that are completely fixed. Those are the green elements here. And you have one part that flexes, even though it's fixed to the ground link at a few places. And that allows you to have some sort of relative motion. And so these types of MEMS accelerometers have dramatically brought down the cost of sensing acceleration, and you now see them available all over the place and used for a wide variety of applications. So to summarize what we've talked about in this video lesson, the first thing to note is that the reference frames were a really critical piece of this. You have to know what is the stationary portion of your sensor and what is the moving portion of your sensor. If you can resolve that problem, then the key challenge is to figure out how to measure the relative motion. For very small distances, you notice that we use a lot of capacitive sensing, while for large distances between the stationary and moving objects or stationary moving portions of the sensor, this is much more difficult to sense. Furthermore, some measurements are fairly easy to make while other ones are hard, and it varies depending on whether you're talking about a linear or an angular sensor. So for the linear side, the acceleration is the easiest to measure. We talked a little bit about how that sensor works, and it works in a relatively inexpensive and compact fashion. For position of something, we need to keep in mind the range and how far we need to measure it. And unfortunately, with a linear motion, we need to have a track or some sort of stationary portion of it that extends for the entire range of it. And so while this technology is relatively well established, it can be expensive. Linear velocity turns out to be the hardest of these because of the substantial distance between the two different sensors. And the ways that we did this was basically using satellites, which have a very well-known stationary location, and we can measure the velocity of something relative to them. Or we invert the system and we put the sensor on the moving portion of the body and look for changes relative to the stationary portion. On the angular side, position and velocity were actually relatively easy to measure with things like potentiometers and encoders, or for velocity gyroscopes, which just takes advantage of a linear measurement that comes about as a result of an angular velocity. And unfortunately, the angular acceleration, is still an unsolved problem, though there are a number of techniques that have been proposed in the literature. So finally, we'll just point out that measurement range correlates a bit to measurement cost, and then the ability to measure something on a transient basis versus a steady basis is also changes how challenging these types of measurements are. And that's it for a quick summary of sensors that allow you to measure motion of objects.